My name is Caitlin Rodriguez Rivera, and this is my Physics 2211 video lab report for Lab 2, Motion of a Falling Object. Here is a table of contents providing an overview of the topics that will be covered in this report. First, I would like to briefly touch upon the procedure in this experiment in which we recorded the motion of a crumpled piece of paper falling from an elevation before constructing two computational models, one without the inclusion of drag and one with, to determine the impact on the motion of an object. The fundamental physics principle of Newton's second law relates the net interaction between system and surrounding to the change in momentum that it undergoes, also known as acceleration, over a change in time. Some formulas of importance within this experiment include the position update formula and the velocity update formula, which can be formed by Newton's second law, that work in concurrence with the initial information gathered from the system's video analysis and properties to provide a basis for the computational models constructed. Some additional important formulas within this experiment include the gravitational force formula, which will allow our computational models to mimic the force of gravity acting upon a system, and the acceleration due to gravity formula that is created by dividing Earth's radius by its mass times the universal gravitational constant. Now we will briefly touch upon drag force, which will be demonstrated in the second computational model. Drag force models the existence of air resistance in which an object falling from an elevation will be hit by an opposing force from air particles, which will continue to hit the front of an object in an effort to slow it down. This opposing force increases as the object gains more speed the longer it falls, until net force reaches zero due to the object no longer accelerating, at which point the drag force will be equal to gravitational force. Here is also the drag force equation where B is a proportional constant that I was able to find through trial and error by comparing the model to the graph generated by my tracker analysis. Next, I would like to discuss my video analysis created on Tracker in which I plotted my coordinate axis to show the object falling in the negative y direction. Toward the middle, on the right-hand side of the video analysis, you will see my coordinate points plotted on a position versus time graph that is sloping in a negative direction, demonstrating the object's fall, along with a table with all the values gathered during the analysis. Then I went on to create a computational model using the starter code provided and inputting some initial information gathered from the return data of my tracker video analysis, such as my system's mass, initial position, and observed start time, along with a calculated initial velocity. I also implemented some adjustments to the calculation loop that would continue until my last observed time, such as applying the momentum principle, which would update my object's velocity and position, and inputting the gravitational force equation that would go into calculating my net force. Here is my second computational model that mimicked the first, except for the inclusion of the proportionality constant this time around, along with the force drag equation. As previously mentioned, the proportionality constant was achieved through trial and error. For my force drag equation, I squared the magnitude of the object's velocity in order to include it in my net force calculation that would then apply itself in the momentum principle and update my object's velocity. Here is a visualization of the system's predicted motion based on the code and the computational models. It can be observed on the graph that all three models follow a similar trajectory. However, the computational model without drag has a steeper slope compared to the other two, given the lack of accounting for drag, which means that there isn't an opposing force acting on gravity and the object is assumed to fall at a faster pace. The computational model with drag seems to line up well with the tracker analysis model except for towards the end, which may have been a result of human error or limiting the data used for my tracker analysis model to only the y values. Now to address some additional questions. First, what does it mean? Here are the velocity versus time graphs predicted by my models with and without drag. Terminal velocity is defined as the maximum speed attained by an object while falling, which is reached when drag force equals the downward force of gravity, therefore making the net force of an object zero and its acceleration zero. The model with drag predicts a terminal velocity given its curve begins to level out around the 0.15 second mark, indicating that the object is heading toward constant velocity. Second, what if? Even if we imagine that the object was initially thrown downward, the terminal velocity would be the same as the case where the object was dropped from rest, given that even though they reach terminal velocity at different times, they are proceeding toward the same terminal velocity. Thank you for watching.